I thought it might be fun to talk a little bit about where I see some important questions of global biogeochemistry. In a very real sense, this is also tipping my hand a little bit of some things that I hope to be able to work on up at the Institute of Ecosystem Studies with slightly more time than has been the case around here. But it also reflects, and I saw this on the 1st of May when we were doing a congressional hearing up in Washington. It very much reflects the injection of biogeochemistry. I didn't think I'd last long enough to see this happen. The injection of biogeochemistry into the policy-making process at the highest levels. I mean, the word biogeochemistry was actually mentioned a couple of times in the hearing the other day by our elected officials without messing it up. So it, in some sense, the kinds of issues that I think biogeochemists need to tackle are some of these big issues that we need to have balanced cycles because policymakers don't like to take action if there's a big residual or a big unknown in a budget. That gives the opposition an out to say, well, you know, why should we do this if we don't understand it any better than that? So there's lots to do, but I've been real happy seeing this elevated to the level that it's become. So, you know, we can look at my favorite picture of the planet from the early Apollo shots that I think made it all worthwhile to go to the moon because it gives a real feeling. I mean, even the flat earthers had trouble with this one. That we're out here on a closed biosphere that has harbored life for some 3.8 billion years. Life is intimately involved with the cycling things between the atmosphere and the ocean and the land surface. Of course, the planet seems to have harbored a fair amount of diversity with ups and downs through geologic time. But now with some reason to say that we're seeing some things that are changing pretty rapidly and changing pretty much as a result of the action of our species on the planet. That's a scary proposition in terms of following our own nest, and one that I think we need to understand well and get on with better planetary stewardship. So I really say that biogeochemistry is in some sense environmental stewardship of our chemical evolutionary environment. Luckily, despite the fact that this is a little fuzzy, the National Academy of Sciences has very much recognized biogeochemistry as one of the grand challenges in environmental sciences for the next several decades. So this is not passed unnoticed at a number of governments. It's fuzzy on the thing. It's not the projector. Now, I put this together a couple of years ago to get some idea of the human impact on chemical cycles in the planet. And you can play with these numbers in a lot of ways. I just picked a few elements of the light end of the periodic table that are in one way or another involved with life, and calculated mostly from the geological literature the rate at which contents of those elements are delivered to the surface of the Earth from volcanic eruptions and weathering and the like. And the exchange of these elements in and out of the atmosphere driven by abiotic processes. For instance, carbon, that would be simply the dissolution of carbon dioxide in and out of the ocean. And biotic processes, that's photosynthesis, land and sea. This was a biotic cycle, so that's not so much exchange with the atmosphere, but what was being taken up and delivered to decomposers every year, and essentially an intra-system cycle. And then the human mobilizations of these. But my favorite two columns are the ones that are over on the right, which is the ratio of, at least my estimates, of human mobilization of things to exchange either in and out of the atmosphere or with the exchange from volcanoes. And there's this last column is probably the most interesting in that sense because there's a lot of big numbers there. In fact, one of the smaller numbers, 0.05 or 5%, is, of course, from carbon. The concern with global climate change from rising carbon dioxide in the atmosphere, which is dominating Washington, D.C. right now, is based on basically a 5% perturbation of the carbon cycle. But look at some of those others, particularly nitrogen right below it, 0.65, 65% alteration of nitrogen cycling on the planet. Phosphorus is huge, although there's not much phosphorus moving in and out of the atmosphere, so that one's probably not quite fair. But right below it, 0.87 sulfur, 87% perturbation of the sulfur cycle from human activities, despite the success of the Clean Air Act and things that have taken sulfur out of the atmosphere. So I want to look at a few of these today. Well, nitrogen and carbon today, where I've spent a lot of my time. I noticed Emily talked me into this, and then she didn't show that. If you fall asleep, it's okay, but I'll have to give her some grief. But it actually will allow me to talk about nitrogen in rivers with impunity. So all of you that have had biogeochemistry from me will recognize a number of these cartoons. And there's no errors or standard deviations or uncertainty on any of these numbers. It's typical of biology. These are all in teragrams, or 10 to the 12 grams of nitrogen moving around on the surface of the Earth in any given year. And this is the nitrogen cycle as best we can estimate it for, let's say, 1700, pre-industrial. Nitrogen delivered to the land surface and the ocean surface in biological nitrogen fixation. Cycling internally, some of it flowing off in rivers, and presumably the rest of it getting denitrified, again, land and marine sediments, and returned to the atmosphere. And the numbers, I think there's no reason to think that those were grossly out of balance in, let's say, a decadal time scale. They may have differed considerably over glacial, interglacial times, but decade to decade, reasonable basis for thinking that there was some kind of balance on this. And then, of course, as many people have pointed out, and I found this just in our closet the other day, cleaning up and moving, that humans began with great enthusiasm to produce industrial nitrogen fertilizer. The first number on any bag is the percent nitrogen in it. You can see it there, guaranteed analysis, nitrate, ammoniacal, and urea nitrogen. And to spread that on the landscape far and wide. In fact, this is trivial compared to what goes on in organized agriculture. And Vaclav Smil has pointed out that we probably wouldn't have gotten to 6.3 billion people, and we certainly wouldn't be feeding them anywhere near as well as we are now if it wasn't for the Haber-Bosch process of nitrogen fixation. This kind of revolutionized how humans have grown crop plants on soils that in most of the world have nitrogen deficiency. Jim Galloway and a bunch of us put together the FAO data for fertilizer production and consumption a few years ago, and projections on in here, and I think there's every reason to think that we have over 100 teragram production, 100 million metric tons of nitrogen fertilizer being produced globally now and spread around the Earth. The other lines are just the different continents. And of course, what that's done is when you combine that with nitrogen that's fixed in air pollution, largely in mobile transport, every one of us as we drive along have NOx coming out of our exhaust pipe. You add 100 teragrams and some air pollution, you get essentially an additional nitrogen input to the cycle here on land of 125 teragrams, and essentially it rivals the biological nitrogen fixation, which itself has been increased with the widespread planting of soybeans and the like. And so you can look at that and say, well, what happens? This is my first sort of big issue for biogeochemistry in the nitrogen cycle. What happens to all that nitrogen? Do we have a good idea of the fate of all of it? And if we don't, that brings my question as to where is the residual? In other words, have we increased the flux to groundwater, to river flow, to denitrification? And if we can get some idea of whether those have been increased, is the delta of the human perturbation roughly explaining where all the industrial production goes? I'm going to argue that we're actually rather poor in putting that budget together. So this is my first question. This will be a question for me at Millbrook. It's a question for various of the labs here. I know the Jackson lab thinks about this, the Bernhard lab thinks about it, others. Where does the excess nitrogen go? There's been this emphasis on ammonia and NOx for air pollution reasons. I think we need to broaden that out a little bit more and think about N2O in particular. The general assumption is that denitrification is good, and that's because everybody has their old intro biology textbook that says denitrification converts nitrate to N2, and that goes off to the atmosphere. And very few of those books consider the intermediate byproduct of N2O, nitrous oxide, as at least a small percent production with its greenhouse warming potential and its potential to destroy stratospheric ozone. So I think that the assumption that denitrification is good needs to be seriously questioned, and I'll predict that, I mean, we've got to get Congress and international policy community through the climate change thing, but I think we're going to see equivalent interest put to the nitrogen cycle in the next couple of decades. So we got some time to do this. Now, the first thing to say is there a potential that a fair amount of this nitrogen might be simply applied on the land and running off in rivers, and Van Bremen and others have worked on the nitrogen flux in rivers fairly extensively. This is one of their better compilations. I think this will make Jim Clark happy because there are at least a few statistics here. But so what, 63% of the variance in the nitrogen content in river flow seems to be explained by the nitrogen that's added to the watershed that river is draining over a range of inputs. And the slope of that line would suggest something on the order of 23% of the inputs running off in runoff as a global average. And of course, it's that kind of number that has allowed various global modelers to essentially predict what the current flow of nitrogen from land to sea is in rivers, and it is more than double what it was pre-industrially. And of course, that's a fate of some of this nitrogen that's delivered to the land surface, and also a cause of a lot of estuarine pollution and river flow problems that we read about a lot. So what am I going to do on this? I don't know of any budget in the nitrogen cycle that's done even the beginning of a job at getting at groundwater, the global flux of nitrogen into groundwater. And yet you go through Illinois and Iowa, there's lots of groundwaters that are actually, there'll be a warning sign that says, do not feed this to young children, nitrate contamination of the groundwater, and lots of reasons to suspect that at least some of the perturbation of nitrogen applied on land may be moving downward. It may reappear later as those groundwaters resurface or maybe are delivered to the ocean in submarine transport, but I don't think we have a very good number on that at all. And it's potentially very large, as you'll see with a couple of seat-of-the-pants calculations that I have for you here. Noland, a couple of years ago, 5 years ago, I guess now, did a survey of all the well waters that have been analyzed in the United States for nitrogen, and plotted this out of probability of nitrate exceeding certain levels and increasing colors. Lots of things that seem reasonable here. The Central Valley of California, with lots of the groundwaters apparently contaminated with nitrate. West Texas, where there's a lot of irrigation culture, particularly of cotton out there. And of course, Iowa, Nebraska, Kansas out there with the bulk of the corn and wheat growing area of the U.S. So lots of areas. Now the assumption here, of course, is that there wasn't any nitrate to speak of in groundwater pre-industrially. Of course, nobody really was around to measure it or had methods of measuring it or cared to measure it or even to drill a well deep enough to have it be an issue. But the assumption was essentially there was no nitrate pre-industrially, and I think you could justify that by finding these very low values in areas that don't have as much agricultural input. And they came up with a median value today for the U.S. of 8.3 milligrams per liter in groundwater. And so this is going to be the grossest kind of calculation, but it's where I want to start with this. The 10,000 cubic kilometers per year, that's an existing estimate of the amount of water that percolates down below the rooting zone of plants globally in all those ecosystems that have an excess of water moving into groundwater. So convert that to liters and put in the 8.3 milligrams per liter for the U.S. You could take a first cut at this and say the global flux to groundwater is 83 teragrams, 83 million metric tons of nitrogen into groundwater. Now, there's all kinds of reasons to say that's probably wrong. Fertilizer use in the U.S. is way higher than the global, although Europe and China are coming on strong with this. And so it can discount that and say, okay, well, just shy of 15% of the runoff of the world runs off of North America. So maybe the first pass at this would be to discount the 83 and say it's only happening in North America, and you come down to something like 12 teragrams. And then you could say, okay, what is the proportion of the fertilizer applied globally that happens in North America? And that's 32 teragrams out of 141, so you can essentially scale it back up and get something like 54. Obviously huge assumptions, huge errors on that, but those are all pretty big numbers. You could put, 83, 12, or 54 there if it used to be 0. All of those are heretofore kind of unappreciated flux of nitrogen into groundwater in the global cycle. I picked the 54 kind of as an intermediate. It certainly needs to be refined, and I think this is something that I will probably devote some time to in the next couple of years to try to work that out. Another flux is this denitrification flux, and I think there's all kinds of reasons to think if you have more mobile nitrogen on the land surface, that a certain portion of that's going to run down into wetlands, be they freshwater wetlands or coastal wetlands, and get denitrified. Essentially, you're feeding them one of the raw materials of that, and we can sort of say what could potentially be the perturbation there. And with that, I want to approach this with the gas nitrous oxide, N2O, which globally seems to be something on the order of 1% of the total amount of material being denitrified, at least in lab studies where people have looked at the total amount of nitrate that disappears in gaseous form. About 1% will come out as N2O. It's rising in the atmosphere. This shows the rise over about a 5-year period as a function of latitude. The rise is faster in the northern hemisphere than the southern hemisphere, and it shows us seasonal oscillation. And those are all things that are kind of indirect evidence that denitrification must be going on here. More wetlands in the north than the south. Seasonal fluctuation would reflect something that is likely to be responding to a warm season and a cold season. You could also say maybe it's the dissolution of gas as a function of temperature, so it's not perfect. But just looking at that record would suggest that something biological is probably likely to be involved with that. And could we translate that into a better estimate of denitrification globally? The ice core records, I think, give a even further substantiation to the idea that something has happened in the realm of denitrification. This goes back, to 2,000 years worth of samples. These are largely from Greenland, done the normal way of taking an ice core, melting it, and getting the bubbles out and analyzing them for N2O. And you can see that within some limit of variation, that the level of N2O was what I'll call fairly constant for nearly 1,700 of those years from these cores. Some of that's certainly analytical variation and measuring it at parts per billion levels in a bubble of several thousand-year-old air. But something strange starts to happen in the late 1800s, early 1900s, which in the concentration begins to rise in the atmosphere. And again, it's correlation evidence that is about the time that the Haber-Bosch process was developed and applied globally. But you can look at that and say, okay, that could reflect the overall perturbation of denitrification, of which This is sort of the 1% that comes out as N2O, and the rest of it is very hard to measure because it's coming out as N2 and the atmospheric background 78%. So you can look at that rise and say, if we know actually the ratio of N2O to the sum of N2 plus N2O, and we know the rate of rise of N2O in the atmosphere, then we could calculate total. And so I've already begun to gather numbers now. This is a biogeochemist nightmare right now. I was hoping that this compilation of numbers would all be very tightly constrained, and that's not what I've been finding. So they're kind of all over the map, but I think there's, and most of these were not gathered with this particular calculation in mind. You can find these buried in tables of studies done for other reasons. But I think there's some reason to believe that this is not something we should give up on, that a larger data set could produce some reasonable median values that could be applied to this, and throwing out some of the extremes there. I just tried a few calculations here that take the rise of N2O in Earth's atmosphere and divide it by the lowest value after throwing out a couple of really low things that look like outliers, and one of the higher values to get an estimate of what the total denitrification might be on the planet. The total perturbation of denitrification due to human activities. And doing that, I have to admit, I just sort of cavalierly picked a number within the range, but it's the low end, and ramped that up from 100 to 115 as denitrification. I have no idea whether that's accurate. I think this is a ripe ground for further investigation, and something that policymakers will be able to use. Either way, if we find that it's a lot, it's obviously going to encourage the management of those wet areas for denitrification as a way of cleaning up the residual, the nitrogen cycle. If it's low, then we need to think about maybe managing the inputs of nitrogen if we're to have any handle on preventing excessive pollution of waters. And of course, another place that nitrogen may go, or may be going, is into the terrestrial biosphere, and we've put a lot of concern into this at Duke Forest with the nitrogen fertilization of the FACE experiment and others. But if you think about nitrogen being deposited out on the landscape, some of that might go into tree growth and soak up and be a fate of that residual in the budget of nitrogen. Of where is the industrial production going? Newt Nadelhofer published a paper in Nature a bunch of years ago now, 8 years ago, that I think was very provocative as to how much of the nitrogen being applied to landscapes is actually likely to end up in plants, and therefore not get to surface water, not get to groundwater, not flow downstream and end up being denitrified. So we looked at studies where labeled nitrogen had been added as an input, a fertilizer input, and then it had also been measured because it was a label. You could find it in the vegetation. And this is the one-to-one line. All the points would lie along that line if all the nitrogen added ended up in the trees, which is, of course, what a lot of people expected for a nitrogen-limited planet. But what Newt found is that in fact, all the data fell in the lower right corner of this, something on the order of only 20%, to take a sort of a wild average of all of those, of the nitrogen inputs actually ended up in the plants, and the rest went somewhere, into the river, into the groundwater, into denitrification. So that's kind of surprising for a nitrogen-limited world. It also means that the biosphere may not be the most important place to look for this added nitrogen that we spread so happily across the landscape. In each case, these are, you can see studies that have gone from a native input to a perturbed input, following along those trajectories. And that brings me to the second element I want to mention, which is the carbon cycle. Because there's been lots of enthusiasm in looking at nitrogen cycling. both purposeful additions of nitrogen to the cycle as well as inadvertent spread of nitrogen through the atmosphere where it rains down in the native natural biosphere, that this would stimulate plant growth and soak up carbon dioxide from the atmosphere that would otherwise contribute to climate change. Now, Nadelhofer's study there suggests that was probably overly optimistic. I'm going to pretty much say I'm in agreement with that. If you're looking to rid the atmosphere of something between 6 and 7 billion metric tons of carbon every year that's released from our fossil fuel activities, and only 20% of what lands on the land surface is likely to end up in plant tissue and stay there, that is 20% of the nitrogen, and you take a reasonable C to N ratio, for instance, something like 100 carbons to 1 nitrogen in plant tissue, you really can't get a whole lot of nitrogen to drive a greater uptake of carbon dioxide into the carbon cycle. But I think the carbon cycle is also a field day for biogeochemistry, at least in the next decade. And in this particular case, the demand for refinement is very real. We got into arguments on Tuesday that were very much pointing the finger as, why haven't you guys done better on this of explaining where the carbon's going? And so there's lots of things to do. At the risk of waxing a little bit historical here, I want to say a little bit how I got into biogeochemistry, and as long as this is kind of a swan song talk here. And I would say that one of the seminal things for me, this unfortunately doesn't have the date on the cover, but it was in 1970. I'm sure Dan remembers this particular issue of Scientific American that came out and has, you can see by the tattered cover of it, my copy has been well used. It has summaries, or it had its summaries of what was known of biogeochemistry at the time. I ran into this in college and had some readings out of it, and I'd say that's where I got interested in sort of, gee, how does the planet fit together, and how do one element control or alter the cycle of another? So there's wonderful chapters in there by Ed Deby and Bert Bolin and others on the Connie Dulwich, who did the nitrogen cycle. And the picture, this is out of Bert Bolin's chapter, that really launched me into biogeochemistry was his picture at the time of the carbon cycle. And I don't know what it, maybe I'm a bit possessed with things decomposing and rotten for a long time, but that box there, dead organic matter, was acknowledged to pretty much be a large unknown in the cycle. And of course, it also simultaneously was one of the larger pools. Bolin estimated 700 billion metric tons of dead decaying stuff globally. And Bill Reiner's convinced me that, in fact, that should be refined. In fact, he tried to refine it for the Brookhaven conference in '72. And so I, in a nerd-like fashion, went to the Cornell Library and spent a lot of time refining it. And if I had to look at one table of data or one compilation that basically I would say, this is what I contributed to science, it would be this one, which came out of my review in 1977 of soils as reservoirs of carbon. And being from Cornell, Whitaker, and Likens, of course, had divided the world up into these categories for their estimates of net primary production, and they'd given the area to them. And I was able to put together the soil content, and that's simply as if you excavated a square meter at the surface down to at least a meter depth and brought it up as a block, how much carbon was in it, and multiply them across, and came out with a number that's essentially twice what Bolin had estimated, and felt quite good about it. And so there you go. That's how I got started. Now, Rob Jackson and others have done this in a much more elegant way in several different compilations. Rob also used different categories of ecosystems. We all agree on the land area involved in the surface of the Earth. That's a number that doesn't have a lot of problems. Rob, looking at the 0 to 1 meter, also came up with something. What I have 1456, you got 1500. For biogeochemistry points of view, that was a wonderful agreement, and of course we all felt good about that. Rob also found considerable carbon that was actually held at below that surface meter, the 1 to 2 and 2 to 3 meter depth, so that the overall pool on land actually was considerably higher than I had estimated. And you can say, okay, what's happening to that deep carbon? It's probably pretty much refractory. But I think that's probably the best compilation out there in the literature now. His was based on several thousand soil cut-ons that had been gathered by Paul Zinke out at UC Berkeley. And anybody who knows Paul Zinke, he's a great guy, but the one thing he never did was publish. And so Rob was able to get into that data set and actually bring it to life, which we can all be thankful for. So where are we with the carbon cycle? These have been, this kind of budget is what I call the atmospheric checkbook. So think of the atmosphere as something that deposits are being made into every year with CO2, and withdrawals are made that go other places, into the ocean or into the land. We could easily do this for the first decade here of this century when it's completed. But what I've got here is in the 1990s. This comes from a compilation of the previous IPCC. So here's fossil fuel emissions to the atmosphere. It's positive. That's a deposit into the checkbook. The atmosphere, the checkbook itself increases by about half of that, 3.2. So that's what stays in the atmosphere. The oceans take up CO2 and perform a big ecosystem service for us by doing so. So that's a minus 2.4. And then there's been this residual, net terrestrial flux. The oceanographers don't want it, and basically say, our measurements are correct. It's got to be with you guys. And so it became known as the missing sink, or the net terrestrial flux. Dave Schimmel calls it the holy grail of carbon cycling, because anybody that finds it will instantly be elevated to great fame and fortune. And Stevie has pointed out that that's the net terrestrial flux globally. It's actually got to be a balance between what we know and can see in remote sensing as a huge emission from tropical deforestation. So that's this land use change term here that's roughly positive. It's going into the atmosphere, 2.2 billion metric tons per year, which means that the residual terrestrial flux has to be bigger than that, so that the terrestrial biosphere is overall a sink. And so they've got a minus 2.9 estimated there, and the assumption is this must be in the temperate zone, where there's some regrowth of forests and management things going on that might allow it. So those are big numbers. You can say if the temperate biosphere is doing that for us today, and these are our emissions, if we don't manage this biosphere well, and appreciate the ecosystem service it does by taking CO2 out of the atmosphere, the rise of carbon dioxide will, the rate of rise will itself increase dramatically. So I think it's important to think about the carbon cycle in those kinds of terms. So these are my questions for carbon cycling, and sort of where is the residual? I'm gonna agree it's probably on land. I'll fold on that. I used to argue with the oceanographers vehemently that it was theirs, but I'll fold on that one. It's probably ours. So it could be vegetation and soil. It seems to be going on now in the temperate zone, minus 2.9. That's the uptake. But could you, if you got interested in this as a policymaker, encourage that to be a larger number? And would it be worthwhile to do so? And I think there's biogeochemists have a lot to say about this. Now, some of the numbers we were arguing about up in Washington earlier in the week were uptake in forests in the United States, and actually probably all of North America. These are numbers that include both vegetation and soil. So they may be slightly higher than some of you that are used to thinking about just the tree component. But the uptake in a growing forest, Duke Forest is a good example, somewhere in the 100 to 500 grams of carbon per square meter per year. A 15 to 20-year-old stand-up loblolly pine in Duke Forest is at the upper end of that range, something on the order of 500 in that. Mark Binford, who was somebody's postdoc here a few years ago, over in the phytontron, was either Jackson or Reynolds. Okay. He just published a very nice paper that used flux measurements over the southeastern coastal plain that integrated, of course, growing forests with mature forests, with parking lots and suburbs, and got kind of a regional average, and it turned out to be about 100 for the coastal plain, ranging from Florida to North Carolina. So you want to look at that uptake. You know, foresters always go out and they like to measure it at nice, good-looking, fast-growing stands. That's not the number to use if you want to get some kind of regional average, and the lower end of that range is probably better. And if you do that, then the total uptake in the U.S. Today is something on the order of half a gigaton. Remember, we're looking for 2.9 in the temperate zone globally. So this would be 0.5, so it's about 15% of the global sink in the temperate zone might be in forest growing in the United States. That has caught the interest of a lot of policymakers who, in fact, has been used as an argument for the U.S. not to have to join Kyoto for a long time, because our commitment was only going to be 7%, and forestry was already doing twice that for us, and therefore we had to do nothing. Of course, the thing to remember, I mean, we all want to be thankful that the forests in North America and Europe and other places where they've been replanted and are regrowing are in fact doing so, because without that, sink carbon dioxide would be rising even faster than it is. On the other hand, you also want to think about the ultimate fate of those forests. They will grow up to a mature state in which the net landscape will probably be neutral with respect to the atmosphere. Some trees will still be growing and getting larger, but they'll be balanced by others that are outcompeted and die and decompose. And the landscape will be close to zero. And at that point, you have no further sink from that regrowth. The only significant long-term sink that derives from this kind of thing is twofold. The first is if you take growing forests and convert them into houses or furniture or coffins or something that's going to stick around for a while, and park the carbon there, and then start a new forest. A paper, a quite nice paper, came out recently that has looked at these long-lived products and found that actually they're very, very small as a component of what we're looking for. You know, 0.006 when we're looking for 2.9. And so the long-life product fate is not a particularly reassuring sink for carbon in the long term. The other thing, of course, is you could harvest them and convert them into cellulosic liquid fuels, or simply use them as solid biomass fuel in place of coal or some other. Anytime that you replace the biomass fuel, you use that to replace fossil fuel, you'd have a net positive impact on the rise of CO2 in the atmosphere. But at least the long-life product thing doesn't look terribly favorable. And that's a message that I tried to carry up to the policymakers earlier in the week, is that we want to be thankful that forests are out there doing what they're doing, but you can't sit here and do nothing and expect that they're going to solve the problem for us as the next few decades play out. We need to very seriously think about cutting emissions or moving to non-carbon type fuels. Mac Post and others, and we've messed with this a little bit too, looked at what goes on in the soil component when you abandon agricultural land and allow it to grow back through secondary succession into forest. Mac gathered a very nice collection of data. I think it's got several hundred studies in it of carbon sequestration that you can expect over a few decades. Comes just shy of 34 grams per square meter per year. Notice it's in the 10% of what you can get into trees. And then multiplied it by the abandoned land in the eastern U.S. and the abandoned land in the world. Those are pretty small numbers. Again, remember, we're looking for 2.9 total uptake. They help, but they're pretty small of that. Rob and I tried a few years ago. We said, okay, we're emperors. We're going to declare that all farmland in the U.S. will be converted from row crop agriculture cultivated to no-till instantly, or retired from agricultural production. What could you get up? What could you take up in soils? And we got what, 0.059, pretty small number. Remember, U.S. fossil emissions, just our country alone, 1.6. That's a totally unrealistic scenario for feeding 6.3 billion people. Then we got really rambunctious and said, what happened if we not only abandoned a third of the farmland, but planted it in plantations so that you had the soil uptake plus the tree uptake? You see a bigger number there. That comes up to about 10% of current emissions. It turns out that the area to do that is roughly the size of the state of Texas. So that would require finding a Texas-sized area that today does not have trees on it, but could grow trees if you planted them, and plant it, and you get that sink up through the maturity of those trees, and then you'd have to either cut it down and put it into furniture, or burn it in power plants, or look for another state of Texas and start over. Crawford would be right in the middle of it. I pulled this out of a paper that Ratan Lal has in Science because I think there's been some fairly disingenuous things said about the potential for soils to soak up carbon. And this was one of them, and there was all kind of irrigating them and restoring desertified soils and better management of crops, and they come up with these huge 0.4 to 1.2 gigatons, something in the order of 10 to 25% of fossil fuel emissions could go into soils. That's optimistic. That makes you feel good, but it also allows policymakers to not really tackle the real issue, which is where all this carbon dioxide in the atmosphere is coming from. And of course, our numbers are coming in many times with 0.0 or 0.00 with the digit, and nowhere near that kind of uptake. A couple of years ago, this was a true influence of the school of the environment on me too, because it almost was environmental economics, a little scary that way. Only I was using carbon as the currency here. But if you fertilized farm fields, for instance, using nitrogen fertilizer, and this was the nitrogen application in a study in Kentucky, well-published study in Kentucky, kilograms of nitrogen added per hectare. This is the sum over 20 years. And then I calculated what I call the carbon dioxide cost of that nitrogen fertilizer. So those were the CO2 emissions in a petrochemical plant somewhere that were associated with the synthesis, bagging, and transport of the fertilizer to the field. Okay, so those went off to the atmosphere. This is the change in soil carbon content. They're all positive. The farmer felt good at the end of the year. I got more carbon in my soil. That's what Washington told me to do, and I deserve the subsidy to having done that. But if you discount the storage in the field, if you discount that by the CO2 that was released in producing the fertilizer, those were pretty substantial discounts, up to 60% in some cases. And this kind of thing needs to be applied more widely on a lot of these management techniques. In fact, this was one of the better studies. I had about 12 or so of these where you could do this calculation, and something on the order of 8 or 9 of them were actually negative. The CO2 released in fertilizer production totally discounted the increase in carbon in the farm field. So this is actually one of the better ones. But again, it's a case where biogeochemistry can be applied to these problems. Now, no seminar here can be given without a little bit talk about the FACE project, because of course one of the things we've been looking there is the sink for carbon in trees and soils. You've probably all heard about the trees ad nauseum, so I won't say much about that. But one of the things we have noticed is that the forest floor, over the course of the first 6 or 7 years of the study, and John Lichter really deserves credit for compiling these numbers and digging the holes to do it. But the forest floor has gotten thicker out there in the high CO2 plots. This was over a 3-year period, so it's been storing carbon at about 60 grams per square meter per year in the undecomposed material on the surface of the soil. The delta C13 reflects the isotopic signature of the fumigation gas that we use to maintain the high CO2 atmosphere. So this is a good C3 plant. Forest floor resembled that in the control plots, but the elevated high CO2 plots are reflecting our depleted gaseous source there. So forest floor is accumulating, and the accumulation seems to carry the isotopic signature of the fumigation gas. That seems to be a pretty good potential sink. Down in the soil, I think Jeff probably dug some of these holes too, but so distinction for the behind the scenes guy here. Here's mineral soil 0 to 15, 15 to 30. No significant changes down there, where a lot of people have expected sinks for carbon in soils down deep. Strangely, at least at the 0 to 15, you can see a significant decrease in the isotopic value of the soil organic matter. So the face fumigation gas signal is getting down there. It's getting into the soil pools, but our interpretation of that is that it must be stimulating the decomposition of pre-existing organic matter so that you can have the isotopic label show up, but no change in the pool. All this has led us to a little bit of discouragement as to how important these soil pools were. Although Julie Jastrow has gathered in a meta-analysis data from all the face experiments she could find where somebody analyzed changes in soil carbon. So these are arranged by increasing length of the experiment. And here we are, loblolly pine in the 6-year category. Here's 0. So these are all studies that showed some gain, even if it was non-significant in the study. In fact, the only ones that are significant are the ones with the stars. It's very typical. People are seeing a little bit of gain, but no statistical significance. A couple of them lost. And in the meta-analysis, she suggests that, in fact, because the statistical power of any one of these experiments is not great, that maybe this is a better thing to follow. And the average was around 20 grams per square meter per year uptake in soil. And so giving Julie the benefit of the doubt, here's a budget that I've liked to show a lot of policymakers as to what the effect of rising CO2 will be on the carbon sink in forests. Remember, we have a sink today of about 500 million metric tons per year. What would be that sink 50 years from now when CO2 is higher? So here's our control plots. Carbon uptake over 500 grams per square meter. It's at the upper end of the range I just gave you, but it includes these soil pools, which basically are the things that push it over the edge. Most of it is in tree trunks. Second column there is what goes on in the elevated carbon dioxide stands. Again, the tree trunks dominate, but the forest floor has shown significant increases. That's the change in grams and the change in percent, and that's highly significant. The soil show little increases that are not significant. Groundwater, an interesting but small significant increase. And overall, the forest 50 years from now, I think we can think about as having perhaps as much as a 35% greater carbon storage going on per square meter per year. Okay, so now I'm a policymaker. Do I care about that? And so I think the calculation that's relevant here is to come back to that 2.9. That's the missing sink that we think is going into the temperate zone today. And then we'll cavalierly say, suppose all that temperate zone forest is going to respond to CO2 the way Duke Forest did, with a 35% increase in carbon storage. That'd be another billion metric tons. So you're up to 3.9. But by the year 2050, emissions have also basically more than doubled. They're up at 15 billion metric tons per year. And so you get the anticipated sink 50 years from now as 6.7% of the emissions 50 years from now, or 12.6% of the change in emissions between today and then. To me, it doesn't matter which of those numbers you use. They're both pretty small. I think a policymaker really can't expect that, let's use 10% for a sort of a mid value there, that this 10% increased carbon storage expected then is going to do a whole lot to prevent climate change between now and then. And so I think that's a way of giving that a little bit of perspective. And so I'll just close by going back to Steve Houghton's budget for the carbon cycle on the planet, because I think it shows two things that I've tried to stress here, these residuals are often critical, and they're often, you know, they're put into the budget as if it was something real. What they really are is a display of our lack of understanding of that particular cycle, and it's where you need to park something to have the budget balance. And so those, when you see a biogeochemical budget with a residual like that, I'd say that's where to do your thesis, and you know, it's where the real questions may come. And the second is that biogeochemistry, I think, will ultimately provide some real constraints for policymakers on the nitrogen cycle, the carbon cycle, mercury cycle, a number of these elements that could be talked about in these kind of terms. When you consider that this uptake, you know, I don't know whether it's 2.9, there's a big error term on it or not, but it's clearly large, and it needs to be managed as an ecosystem service that nature performs for humanity. So I will stop there. Thanks for all for coming. It's actually been great fun being around this group for the last 27 years, you know, teaching biogeochemistry and working on a bunch of these things with lots of folks, which I will miss. But we have things we can all do here and at the Institute of Ecosystem Studies on into the future as well. So thanks.